In this video, we'll look at reactions at the benzylic position. And these will be reactions that we've already seen before, but applied to the benzylic position. So when I have a benzene ring, the position next door to it is the benzylic position. So this carbon right here is the benzylic position. And it has a certain reactivity because it's adjacent to that set of double bonds right there. So, some reactions we've seen before are dehydration reactions and also dehydrohalogenation reactions. So I just want to show you the example that if I have a alcohol, say, and it's adjacent to this allylic position, whatever the other substitution is, so I'm going to make this, more substituted over here, it's still only going to give the double bond that's at the benzylic position, so adjacent to the benzene ring, and that's because now you have a conjugated system. So this is done using H+ and heat. We already know the mechanism for this, but the only product that we see is this, because you have this whole conjugated system. So a dehydration, if it's possible, adjacent to a benzene ring to give a conjugated system where there's a lot of p orbitals in a row there, and resonance stabilization is possible, that's the only product you'll see. So in this case, the only product we see is the conjugated product in a dehydration reaction, which is just the loss of H2O. The same thing is applicable in an analogous dehydrohalogenation system, so we'll use the same starting material but with a bromine this time. So of course I would need basic conditions here. We'd need a strong base, and again the only product I would see is that conjugated system that gives me conjugation throughout. So this is my only product, and this is a dehydrohalogenation. So minus HX, X being the halogen and H being the hydro part. We can also think about the reactions that we've previously learned with respect to alkenes, and because of the inherent stability of the benzene ring, it's not going to react under the same conditions that just the average alkene would. So I'm going to put in a series of different reaction conditions. So for example, hydrogenation we've seen with palladium. We've added Br2 across a double bond. We've added HCl across a double bond. And another example would be like HBr and peroxides. What happens is in all of these cases, it is only going to react with this alkene that is outside of the benzene ring. It will not react with any of the pi bonds in the benzene ring because of that stable conjugated system. So the products of all of these are going to be just that terminal alkene reacting. So HBr and peroxides gives an anti-Markovnikov of HBr, so that addition gives the bromine on the less substituted carbon. HCl would give me a Markovnikov addition, so I'd have Cl at the more substituted carbon, H at the less. The hydrogenation reaction would add H2 across the double bond. It'll do that across that double bond outside the ring, but not the one inside the ring. And then also Br2 gives me addition of 2 bromines, one at each carbon across that double bond, but it will not disturb the actual pi system in the conjugated ring. So it's only pi bonds that are outside of the aromatic ring that will react under those normal alkene reaction conditions. If we want to have the aromatic ring react, there's more sophisticated and activating conditions that allow for that reaction to occur. And then lastly, analogous to allylic halogenation, we have benzylic halogenation, which is just the reactivity of the benzylic position outside of the ring. So here I would have this position here that is adjacent to the ring. That's my benzylic position. And if I put X2 in heat or light, I get X connected to that benzylic position. So if we think about what's happening here, we would have this carbon with a couple H's coming off of it, and let's use Br as an example. The bromine would abstract the hydrogen atom to give me, I'm going to do HBr as my byproduct, plus, and then I'll go to the next slide. Now I'd have a radical at the benzylic position, and that can go all the way around the ring. So it's adjacent to the ring. So now we have our radical inside the ring, and that's going to get kicked all the way around just like every other intermediate we see. Remember single-headed arrows because we're moving one electron at a time. Then you can essentially get back to the beginning. So my pi bonds have all shifted over one. And my radical's back out here, and then that radical will abstract a bromine atom to give me that final product with the bromine at that position. It will not disturb aromaticity though again. So even though we have resonance structures where the radical is stabilized around the ring, the only place that we'll see that substitution is outside of the ring. So the bottom line is all the reactions you know that apply to allylic systems or alkenes on their own don't apply to the benzene ring. It's a specific activated set of conditions that we use in order to get the benzene ring to react because it is more stable and therefore less reactive.